convert a 200 amp 120/208 single-phase panel to 208/240 single-phase, a step-up transformer is necessary. The apparent power in kilovolt amps, abbreviated as kVA, is calculated using the formula kVA equals voltage in volts multiplied by current in amps. For a 120/208 volt system, the kVA is calculated as the sum of 120 volts and 208 volts multiplied by 200 amps, which equals 67.2 kVA. For a 208/240 volt system, the kVA is calculated as the sum of 208 volts and 240 volts multiplied by 200 amps, which equals 89.6 kVA. To convert the voltage from 120/208 volts to 208/240 volts, a 67.2 kVA transformer is required. This transformer should have a primary voltage of 208 volts and a secondary voltage of 240 volts. This setup will provide the necessary voltage step-up to power the 208/240 panel. Buck-boost transformers are generally used for smaller voltage adjustments, typically around 10 to 15%. They are not suitable for large voltage conversions such as this one. Therefore, to convert a 200 amp 120/208 single-phase panel to 200 amp 208/240 single-phase panel, a 67.2 kVA transformer with a 208 volts primary and a 240 volts secondary is needed to provide the required voltage step-up for the new 208/240 panel. This involves understanding the kVA requirements of both the existing and the desired voltage configurations. The formula kVA equals voltage times current is crucial for determining the appropriate transformer size. For the 120/208 volt system, the calculation involves summing the two voltage values and multiplying by the current. Similarly, for the 208/240 volt system, the same principle applies. The transformer selection process hinges on choosing a unit that can handle the required kVA and voltage transformation. A transformer with a 208 volts primary and a 240 volts secondary is specifically designed to step up the voltage from the lower to the higher value. It's important to note that buck-boost transformers, while useful for minor voltage adjustments, are not designed for significant voltage changes like the one described. They are typically employed when only a small percentage increase or decrease in voltage is needed. Therefore, a dedicated step-up transformer of the appropriate kVA rating is the correct solution for this type of voltage conversion. This ensures that the new 208/240 panel receives the correct voltage level for its operation. By using a 67.2 kVA transformer with the specified voltage ratings, the conversion from 120/208 volts to 208/240 volts can be achieved safely and effectively. Remember to always consult with a qualified electrician when working with electrical systems and transformers. Ensuring proper installation and adherence to safety standards is crucial for the safe and reliable operation of electrical equipment. First, understand the difference between a buck-boost transformer and a standard step-up transformer. A buck-boost transformer is designed for small voltage adjustments, typically used to correct voltage sags or surges by a small percentage. A standard step-up transformer, on the other hand, is designed to significantly increase the voltage level. Second, calculate the apparent power, or kVA, required for both the input and output sides of the conversion. The formula for single-phase kVA is voltage multiplied by current. In this case, you need to calculate the kVA for both the 120/208 volt side and the 208/240 volt side. Third, determine the appropriate transformer size. The transformer must be able to handle the load current at both the input and output voltages. Since you're dealing with a 200 amp panel, the transformer needs to be rated to handle at least 200 amps at both the 120/208 volts and 208/240 volts levels. Fourth, select a transformer with the correct primary and secondary voltage ratings. The primary voltage should match the existing 120/208 volts supply, and the secondary voltage should match the desired 208/240 volts output. Fifth, consider the transformer's impedance. The impedance of the transformer affects the voltage regulation and short-circuit current. Make sure the transformer's impedance is compatible with the existing electrical system. Sixth, factor in safety considerations. Always follow local electrical codes and safety guidelines when working with transformers. Use appropriately sized conductors and overcurrent protection devices. Seventh, consult with a qualified electrician or electrical engineer. They can help you select the right transformer and ensure that it is installed correctly and safely. Eighth, remember that buck-boost transformers are not suitable for this application. They are designed for small voltage adjustments, not for large voltage conversions like this one. Ninth, the correct transformer will have a primary voltage of 208 volts and a secondary voltage of 240 volts, with a kVA rating of at least 67.2 kVA. 10th, always double-check your calculations and consult with a professional to ensure the safety and reliability of the electrical system. When you're dealing with electrical systems, especially when converting voltage levels, safety should be the top priority. It's crucial to understand the fundamental principles of electricity and how transformers work. First and foremost, remember that electricity can be dangerous if not handled properly. Always turn off the power to the circuit you're working on before starting any electrical work. Use appropriate personal protective equipment such as insulated gloves and safety glasses. Second, ensure that you are familiar with the local electrical codes and regulations. These codes are designed to protect people and property from electrical hazards. Adhering to these codes is not only important for safety but also for compliance with legal requirements. Third, understand the purpose of a transformer. A transformer is a device that transfers electrical energy from one circuit to another through electromagnetic induction. It changes the voltage level of the electrical energy, allowing it to be transmitted over long distances more efficiently and then step down to a usable voltage level for homes and businesses. Fourth, choose the correct type of transformer for the application. As mentioned earlier, a buck-boost transformer is not suitable for a large voltage conversion. A step-up transformer is required to increase the voltage from 120/208 volts to 208/240 volts. Fifth, calculate the kVA rating of the transformer. The kVA rating is a measure of the transformer's apparent power, which is the product of voltage and current. The transformer must be able to handle the load current at both the input and output voltages. Sixth, select a transformer with the correct primary and secondary voltage ratings. The primary voltage should match the existing supply voltage, and the secondary voltage should match the desired output voltage. Seventh, consider the transformer's impedance. The impedance of the transformer affects the voltage regulation and short-circuit current. Make sure the transformer's impedance is compatible with the existing electrical system. Eighth, use appropriately sized conductors and overcurrent protection devices. The conductors should be rated to carry the load current, and the overcurrent protection devices should be sized to protect the conductors and equipment from overloads and short circuits. Ninth, ensure that the transformer is properly grounded. Grounding provides a path for fault current to flow back to the source, which helps to protect people and equipment from electrical shock. 10th, consult with a qualified electrician or electrical engineer. They can help you select the right transformer and ensure that it is installed correctly and safely. Their expertise is invaluable in ensuring that the electrical system is safe, reliable, and compliant with local codes and regulations. In summary, converting a 200 amp 120/208 volt single-phase panel to a 200 amp 208/240 volt single-phase panel requires a step-up transformer with a kVA rating of at least 67.2 kVA. The transformer should have a primary voltage of 208 volts and a secondary voltage of 240 volts. Buck-boost transformers are not suitable for this application. Always follow local electrical codes and safety guidelines when working with transformers, and consult with a qualified electrician or electrical engineer to ensure the safety and reliability of the electrical system. The task involves changing the voltage supplied to an electrical panel while maintaining the amperage. The key is understanding that a transformer is needed to accomplish this voltage conversion. Here's a more detailed breakdown. Firstly, understanding the existing system. The existing panel is a 200 amp 120/208 volt single-phase system. This means that the voltage between each hot leg and neutral is 120 volts, and the voltage between the two hot legs is 208 volts. Secondly, understanding the desired system. The goal is to convert the panel to a 200 amp 208/240 volt single-phase system. In this configuration, the voltage between each hot leg and neutral would be 120 volts, but the voltage between the two hot legs would be 240 volts. Thirdly, transformer selection. A transformer is required to step up the voltage from 208 volts to 240 volts. The transformer must be sized appropriately to handle the load current. Fourthly, kVA calculation. The apparent power, measured in kVA, is calculated using the formula kVA equals volts times amps divided by 1000. In this case, we need to calculate the kVA for both the input and output sides of the transformer. Fifthly, input kVA calculation. The input voltage is 208 volts and the current is 200 amps. Therefore, the input kVA is equal to 208 volts times 200 amps divided by 1000, which equals 41.6 kVA. Sixthly, output kVA calculation. The output voltage is 240 volts and the current is 200 amps. Therefore, the output kVA is equal to 240 volts times 200 amps divided by 1000, which equals 48 kVA. Seventhly, transformer rating. The transformer must be rated to handle at least the larger of the input and output kVA values. In this case, the transformer should be rated for at least 48 kVA. However, it is always a good idea to oversize the transformer slightly to account for future load growth and to improve efficiency. Eighthly, primary and secondary voltages. The transformer must have a primary voltage of 208 volts and a secondary voltage of 240 volts. This will ensure that the voltage is stepped up correctly. Ninthly, buck-boost transformers. Buck-boost transformers are typically used for small voltage adjustments, such as increasing or decreasing the voltage by 10 to 15%. They are not suitable for large voltage conversions, such as the one required in this case. Tenthly, wiring and installation. The transformer must be wired and installed correctly by a qualified electrician. This will ensure that the transformer operates safely and reliably. The electrician will also need to ensure that the wiring is properly sized to handle the load current. Always consult with a qualified electrician or electrical engineer to ensure the safety and reliability of the electrical system. Converting electrical panels and working with high voltages can be dangerous, and it is important to take all necessary precautions. Here are some safety considerations to keep in mind when working with electrical panels. Firstly, to energize the circuit, always turn off the power to the circuit you are working on before starting any work. This can be done by switching off the circuit breaker or removing the fuse that supplies power to the circuit. Secondly, verify the circuit is to energized. Use a voltage tester to verify that the circuit is to energized before starting any work. This will help to ensure that you do not accidentally come into contact with live electrical wires. Thirdly, wear appropriate personal protective equipment. Wear appropriate personal protective equipment, such as insulated gloves, safety glasses, and a hard hat when working on electrical panels. This will help to protect you from electrical shock and other hazards. Fourthly, follow local electrical codes. Always follow local electrical codes when working on electrical panels. These codes are designed to protect people and property from electrical hazards. Fifthly, do not work alone. Never work alone on electrical panels. If something goes wrong, it is important to have someone else there who can help you. Sixthly, use the correct tools. Use the correct tools for the job. Using the wrong tools can damage the electrical panel or cause you to be injured. Seventhly, inspect the electrical panel before starting work. Inspect the electrical panel for any signs of damage, such as cracks, corrosion, or loose wires. If you find any damage, do not work on the electrical panel until it has been repaired. Eighthly, label the wires. Label all of the wires before disconnecting them. This will help you to reconnect the wires correctly when you are finished working on the electrical panel. Ninthly, double check your work. Double check your work before turning the power back on. Make sure that all of the wires are connected correctly and that there are no loose connections. Tenthly, test the circuit after you have finished working on the electrical panel. Test the circuit to make sure that it is working properly. This can be done by using a voltage tester or other testing equipment. Furthermore, always consult with a qualified electrician or electrical engineer if you are not comfortable working on electrical panels. Electrical work can be dangerous, and it is important to have the necessary knowledge and skills to do the job safely. When selecting a transformer for this type of voltage conversion, several factors should be considered in addition to the kVA rating and voltage ratios. Firstly, efficiency. Transformers are not perfectly efficient, and some energy is lost as heat during the transformation process. The efficiency of a transformer is the ratio of the output power to the input power, expressed as a percentage. Higher efficiency transformers will waste less energy and save money on electricity bills over the long run. Secondly, impedance. The impedance of a transformer is the opposition to the flow of alternating current. It is expressed as a percentage of the transformer's kVA rating. The impedance of the transformer affects the voltage regulation and short-circuit current. A transformer with a lower impedance will have better voltage regulation but will also have a higher short-circuit current. Thirdly, insulation class. The insulation class of a transformer is a measure of its ability to withstand high voltages. The insulation class is expressed in volts, and it indicates the maximum voltage that the transformer can safely operate at. Fourthly, cooling method. Transformers generate heat during operation, and they need to be cooled to prevent overheating. There are several different cooling methods, including air-cooled, oil-cooled, and water-cooled. The cooling method that is chosen will depend on the size and application of the transformer. Fifthly, enclosure type. The enclosure type of a transformer is the type of enclosure that it is housed in. The enclosure type protects the transformer from the environment and provides a safe working environment for personnel. There are several different enclosure types, including open, ventilated, and enclosed. Sixthly, standards compliance. Transformers must comply with a variety of standards, such as those from the National Electrical Manufacturers Association, abbreviated as NEMA, the Institute of Electrical and Electronics Engineers, abbreviated as IEE, and the American National Standards Institute, abbreviated as ANSI. These standards ensure that transformers are safe and reliable. Seventhly, harmonic distortion. Transformers can generate harmonic distortion, which is a distortion of the sinusoidal waveform of the alternating current. Harmonic distortion can cause problems with other electrical equipment, and it should be minimized. Eighthly, inrush current. When a transformer is energized, it can draw a large inrush current. This inrush current can trip circuit breakers and damage electrical equipment. It is important to select a transformer that is designed to handle inrush current. Ninthly, audible noise. Transformers can generate audible noise during operation. The amount of noise that a transformer generates will depend on its size, design, and operating conditions. Tenthly, cost. The cost of a transformer is an important factor to consider. The cost of a transformer will depend on its size, features, and performance. It is important to compare the costs of different transformers before making a purchase. Furthermore, consider the long-term costs, such as energy efficiency and maintenance, when making a decision. Choosing a transformer with the right specifications and features will ensure that it operates safely, reliably, and efficiently. Also remember that proper installation and maintenance are essential for the longevity of the transformer. Regular inspections and maintenance can help to identify and prevent potential problems. Always consult with a qualified electrician or electrical engineer for assistance with selecting, installing, and maintaining transformers. Their expertise can help you to make informed decisions and ensure the safe and reliable operation of electrical systems.